Now, I'll ask you a very important question, a challenging question, which you probably don't have the answer. Did you validate the rotational sequence of your red, yellow, and blue phases?
Does that mean did I make sure that I had them?
Do we have a clockwise rotation or a counterclockwise rotation?
That was something that I really didn't know how to validate it.
There's several ways to do that. One, you can always take an oscilloscope.
Okay.
Set one as one of your phases as a reference, and then take a look at the voltage on each of the other two phases.
Mm-hmm.
Oh, so we totally didn't even, wow. So what you're saying is,
What are some other methods?
You can actually put together an inductor, capacitor, and a light bulb and be able to tell as well.
How would that, how does that work? Because I'm assuming it has, let's see if it was just a,
Well, that's the basic circuit, an ungrounded neutral point, but you have unbalanced load here.
Mm-hmm.
And I'll let you build, once we go through the one-line diagram here, take that home and do the one-line, or do, not the one-line, but the phasor diagram for this, and figure out what happens when you have a positive rotation and a negative rotation of your sequences. And what you'll find here is that because of the inductance and capacitance, the voltage or the neutral point will swing, and you'll get different response on your lamp based on what's happening with your sequence.
So you're talking about current flow?
Yeah. So basically this acts like a resistor, but also acts as an indicator.
So if I didn't do the lamp, if I just put a resistor,
yeah,
then I could measure current flow to find the same information.
That's right.
So we just connected it the way that it was in the diagram. We didn't verify.
That's perfectly fine.
But I'm assuming.
Well, that's if you want a perfectly correct answer. We could make the assumption and just do it mathematically here.
So what I assumed it was that
Positive sequence?
Yeah, positive sequence, kind of like in the pre-lab, it explained that we were doing ABC, and A corresponds to the red, B corresponds to the blue, and C corresponds to the yellow lines down there, because the yellow, in the way we were configuring it, was where both of the watt meters were connected to.
Okay, that's fine.
The voltage.
Now,
I had another question that perhaps we can answer during the class period was when I decided, I did a voltage to neutral test, and we were at 118, 117, and then the third one was at right at about 100 or 90, 98, 100. 101, that's what it was.
okay.
So why is that?
Because the building is loaded up and there's imbalances in the system. And they'll cause different voltage drops on each of the three phases, unbalanced loads.
So I was under the impression we weren't actually pulling three phases in.
We're not. We've got two plus the neutral.
Creating the third, right?
Mm-hmm. But the two phases relative to neutral are not constantly at 120 volts, as you probably have noticed.
What's that type of arrangement called where you use the two phases?
Scott T.
A what? A Scott T?
Scott T transformer connection. All right. Let's assume that the rotation is this way.
Okay.
All right. Now, we should be able to figure out what the current flow is with our capacitive circuit, right?
Yes.
All right, so if we look at it from V over Z standpoint, our current, did we calculate the current anywhere?
Not on mine, no.
Okay, but we do know what the impedance is. So let's do 171 at an angle of 82 degrees.
Isn't it gonna be
And it's
negative? Yeah.
negative because we've got a capacitor there. We'll just keep 120 here for the time being.
Oh, yeah.
So we should be able, and we'll set this at 0 degrees, being this phase A to neutral. And so this is the load between A and neutral. So what's our current?
So it's 120 divided by 1071 is 0.112 at an angle of 82, positive 82, right?
Okay. So we'll have a current here. It's going to be 82 degrees. So this is IA. All right. Then we should be able to figure out B and C currents. IB should be down here. And IC should be about there.
Okay.
If we were doing the inductive load, wouldn't those be swapped?
Yeah.
Yes.
Because that's the one that we drew out, was the inductive one.
Okay.
All right. What else did you need?
So that will find us power, the S, in each
Okay.
load, right? Because we have the phase voltage and the current in the line.
Uh-huh.
Both. Yeah.
So let's put Q and P diagram here. So we put the relative current, so our voltage is going to be used as a reference. So we can put our voltage here for a moment. Multiply that by a factor of, one of these by a factor of 3 to take care of the fact that we've got our 3 phases. And we'll multiply the vector by -3. All right.
And the angle in between them is 82 still.
Still 82. So, of course, the real power is the projection onto the x-axis. So this would be P. Now, we've got to take the conjugate of that. So this would be the value of Q, but we've actually got to take it below here. So this should be on the order, what did we calculate that out to be?
Oh, sorry.
36 bars. This came out to be 5, but we now need to multiply that by a factor of 3 for all 3 phases.
So I can see how you get the P, but the Q, you just like flip it down and.
Well, remember, here's the current, but we got to take the complex conjugate so it reflects along the x-axis.
Okay. And then you just take the Y component.
Then we take the y component of that.
Okay. Jeremy, you're taking a video of this, right? Okay.
Yes.
Well, they haven't been turning out real well.
Okay, I'm gonna take a
Yes,
picture.
because you got 36
Yeah,
bars
pictures are definitely
in
good.
each of the phases.
I don't have a very good camera.
I get it.
Reactive power. Yes.
Okay. And so that gives us power. So would you say so S is just the inverse conjugate of the current then?
Basically, yes. The complex conjugate of the current is going to be the angle of the power, complex power. Now per unit, with voltage going to 1 per unit, then magnitude-wise, they'll be the same,
Okay.
which makes it very nice for working with per units.
Okay. And so how does that, where do we put the power on our nice phasor diagram over here?
Well, you got to have basically two, because remember, it's the angle difference between our two phases, between our current and our voltage on each leg of our phases.
Okay.
And so,
And that's, all of them are 82,
yes.
right?
So we really had to build a separate diagram for the power versus.
So, I mean, to me, it looks like with this diagram, we can say that the magnitude of the power is the same as 3 times the magnitude of the current. That doesn't make a lot of sense.
No, remember we got the voltage relationship between the current and the power. Yeah. The voltage changes the magnitude of the power relative to the current.
So,
You still obey the basic law that S is equal to voltage times current. If the voltage is set at an angle of 0 for convenience, and we call that we've got to take the complex conjugate of the current, so whatever angle phi is, or actually that angle we'll call theta. That's going to be the angle theta seen by the power. But that's also the same, and this would have a negative sign in front of that, and that's also the same as the impedance angle. So the angle of the impedance matches the angle of the power. And the current, if the voltage angle is set at a 0 reference, is the negative of that theta.
so is the magnitude of the non-conjugate, like the normal IA, I mean, is that the magnitude of IA, or is that 3 times the magnitude of IA that we're
No, this is IA. We moved it over here and multiplied by 3 IA so that we took into account IC and IB.
But doesn't that just conjugately reflect the magnitude of the 3 times 36 R and 5 times 3 watts?
So basically this becomes minus 82 degrees, and the length here is 3 times, so
But that's the S right there, the magnitude of S.
yes,
correct?
this is S right there.
Which is, so is the, I guess my question is the var, is it just the negative of the y-axis of the IA, does that make sense? Because the power is directly corresponding, obviously.
Yes.
But so is the var, or is Q, the negative Q, is that the same magnitude as the positive Q?
Yes. But we have to take the complex conjugate.
Yeah. So then, from that, if you have the same y in the positive and the same y in the negative, and the same x coordinate, then you have the same magnitude of both S and IA. And 3IA.
3IA plus, this also gets multiplied by VAN.
Okay, so that's not just IA, that's IA times V.
Yeah, but from a vector standpoint, yeah, we're showing the more of the angle aspects, yes. But you would multiply the voltage, so it's going to give you the length of the vector.
So if we were to calculate, there was 2 powers that we needed to calculate, right? So there's the power of the voltage phase to neutral times the current multiplied by the cosine of the phasing plus 30. So would it be this 82 plus 30 and 82 minus 30?
I think you got some things confused on that one.
How would you calculate?
Why don't we talk about that one after class? See what you were actually doing
Okay, so
later today then.
on the lab, it says draw a phasor diagram, three-phase power system under test, and indicate on the diagram the readings of each of the two single-phase watt meters on the diagram. Now, we have not even shown what the watt meters are reading because we would need to multiply VAC by the current in IA, right? And that gives us the watt meter reading. Is that correct?
Yes.
So we would need, so to be very complete on the lab, we were probably going to need 3 phasor diagrams for each thing. One that shows us this, another that shows us the actual power in each phase, and then one that shows us the readings on the watt meters. Probably something along those lines, just to understand everything.
Yeah, because actually, yeah, let's put up our 3-phase line-to-line voltages.
Okay.
Let's choose color that's we can work with. Let's use green in this case. Assume positive rotation, so basically now we're sitting here at VAB, VBC, VCA.
Okay, so if I understand correctly, the watt meters are reading from CA and BC, so we're not even going to use VAB with the watt meters.
All right, let's check this. Let's label this A, label this B, and label this C, right?
Oh,
We had a
so
label
you have
differently.
them labeled differently.
Oh, okay.
See.
So that was C, yeah.
Okay. Then it's going to be a little different than how I normally calculate it.
No,
Still
that's
can be
fine.
done.
We can do it how you normally calculate it. You can change whatever you want.
To make life easier, we
Yeah.
usually put B here
Okay.
and C. But it does,
Like
if
this.
you do the phasor diagram, it's still going to come out.
Okay, so B is the one that both of the
Right.
watt meters are connected to. They're
Yes.
okay.
So we're using V.
Line 2.
The
C.
one.
Yes, so basically here we're reading voltage VAB in this case. And here we're reading the voltage VCB.
BCB.
Yeah.
Okay, so we don't currently have that one up.
No,
No, we're okay.
but let's see, we're VCB should be the opposite of VBC, right?
So it would be pointing up from there.
Okay, so we're really working with this voltage here and this
That
voltage here.
And you're working with current IA and current IC. Those are voltages.
Oh, sorry. IA and IC. Okay, so let's draw another phasor diagram that just shows those components. Nothing's changed, we're just moving these over here so we can look at them.
Okay, yeah.
Okay. Let's make sure our angles are correct. So given a reference here, this is 30 degrees.
Okay.
This is going to be 82 degrees. This is going to be, ends up being 90 degrees.
That's
Right.
9.
Well, 30 plus 82 is not, well, that gives us more than 90. 30 plus 82, we end up with
No.
112.
It's
Oh,
How
you're
would
saying that's
you-
inclusive of the 30.
Yeah. Yeah, 82 has the 30 in it.
Okay.
within it, yes. Remember, it's from our 0 degree, which was voltage at phase A to neutral.
Okay, yeah.
Okay.
VCB should be at 90 plus 90 degrees.
Because that's not VBC. It's VCB.
VBC is at minus 90 degrees.
Yeah, okay, I can see that.
So
Okay, I get
if we
that.
keep tilting around, then will we get we'll get VC to neutral? Would be the next vector.
Actually, voltage of C to neutral we won't use because what we measured is
This is the,
C to B in your meter. Right?
yeah, we're just putting the diagram of what the meters are seeing right now.
That's right.
Okay.
Well, and then this one would be, this is 82 has VC, but VC is 120 degrees. So 120 plus 82, that should then be 202 degrees.
Okay, so just to make sure I understand that again. We know that from VA neutral to VC neutral is 120, and we know from VC neutral to IC is 82, so it's just 120 plus 82. Okay. Okay, I get that.
Okay?
Yeah, sorry, I just had to work that through real quick.
All right. Now, we go back to our meters here. So we're measuring power equals to voltage magnitude times current magnitude times cosine of the angle theta between the voltage measured and the current measured. That's what the meter does, right?
Yeah.
Okay, so in this case, we have our first power, P1. That's going to be equal to VAB times IA times cosine.
Between them.
Which is gonna
Yes.
be
82 minus 30 degrees.
52.
Okay, 52 degrees. P2 is going to be VCB
IC,
IC
cosine of 202 minus 90.
Which is 112.
Yeah.
Now, do you see why that second meter is going to read negative?
Because that
Yeah.
returns a negative value.
That turns in there.
Okay.
So what we did.
So we have to switch the leads around and temporarily make this a VBC, for example. That will introduce,
You just slap a negative on it.
and yes, and slap a negative in front of that. So that kind of reverses the cosine, so it's between 0 and 90 degrees.
Okay, so, and that is happening because we have a capacitive load on this.
That's right.
If it was inductive, P1 would probably be the negative,
Yes. No, not necessarily.
not necessarily.
Let's go back and do it from a resistive standpoint. Solve the resistor first,
Okay.
and that will be a lot easier. Now, if we look at a pure resistance, let's put those current values in. The voltage is not going to change, right?
Yeah, the voltages are all the same because they're just line-to-line voltages versus everything else. Now, the currents are going to be along VA and VC.
All right. So this becomes IA,
Uh-huh.
and IC would be here.
Uh-huh.
We now look at our angles. All right, so this is
That's 30.
30 degrees,
This is purely resistive.
90, 120 degrees.
So you have 30 degrees between both of them, so it'll be cosine.
Actually, this one's going to be minus 30, or, yeah, this,
Cosine 30, cosine minus.
No, that's cosine, that VCB times IC is going to be cosine of 30, and VAB times IA is going to be cosine of negative 30.
that's right, one of these has a negative sign. So this goes to
Negative 30.
minus 30. This becomes positive 30.
And that's the same thing, like the cosine.
So that's why we got identical power readings.
Yes.
So this is the resistive one.
All right. Now, we know VA, let's go back. We know that the total power is going to be equal to the power in phase A, the power in phase B, plus the power in phase C.
Mm-hmm.
That's actually, if we take it and look at it from a total three-phase power, we know that this is going to be square root of 3 times VAB times IA, right? Or it's equal to 3 times VAN times IA, right? Where these are just magnitudes. And cosine of 0 degrees, because we're working with a resistor. All right, now let's see what happens over here. We have the magnitude of VAB. Remember, these are all magnitudes. So we have, in essence, 2 times, because it's P1 plus P2, times VAB, being the same magnitude as VCB, times the current IA. Now we have cosine of 30 degrees. So what's the value of cosine of 30 degrees?
0.86.
All right, 0.866
Cosine.
times by 2 should give you 1.7.
Yeah.
And if you square 1.7, you get a value of
3.
So it's the square root of 3. So 2 times cosine of 30 is the same as square root of 3, so that becomes square root of 3 times VAB times IA.
Well,
Now you were able to just do like P1 plus P2, that's all.
Yes, took the 2 meter readings and
just
added them together.
Now you got rid of IC and VCB just because you said that they're going to give you
The
the same.
magnitudes are equal to each
Yeah,
other.
the magnitudes are equal to each other, so that's fine. But in a capacitive or an inductive, they're not going to be equal, and then it gets a little more complicated. Okay, just making sure I had that concept right. Okay, yeah.
Family race.
Okay.
So who has not been down to the lab to do this? So everybody's been down there and played with it now?
Yeah, I think everyone's been down and played with it. It's just the concepts and the calculations that personally I was struggling with. We took all the measurements.
Sometimes when you would plug the machine up, it wouldn't. I don't know, I was helping another group last night and it wasn't reading anything, and it was set up exactly like we'd set it up.
There were a couple
earlier.
fuses. One,
What was that?
Yeah, some fuses were blown. We pulled the fuses out.
we had to like take fuses from the inductor.
Yeah, exactly.
So who's blowing fuses, I wonder?
I don't know. When we got there, they were blown. So
supervision.
there was just 2 of them last time I checked, and so we kind of like left them sitting in there.
Yeah, there's a couple fuses that were pulled out when we went in, but we still couldn't get the watt meters to work, because we got it to work without the watt meters plugged in, but as soon as we hooked up the watt meters, we weren't getting any current or anything through the system.
Make sure that when you push in the watt meter, those banana plugs are very stiff, and you've got to push them deep into the other banana jacks to make electrical connections.
Yeah. That was one of our problems, is we weren't getting a continuity throughout the
Yes.
entire system, so we had to work on that.
Usually good to get, with the power disconnected, use your multimeter in the conductivity test mode and ring out your system, make sure all your wiring elements get connected well. So unfortunately it's like there's 2 standards or 3 or 4 standards for banana jacks and plugs. So
And they're not all compatible.
they're not all compatible, which is strange because bananas have been around a long, long time. All right. Questions on homework?
I don't think anybody's looked at it yet.
Are we supposed to be on, because I know which one says do, but which one we actually do?
Yeah.
Should be worth, you should almost be able to finish 5-1 assignment up. It was, I think, officially due on Tuesday, but we had not covered all the material
That's
yet.
homework 8 and homework 9.
Okay, homework 9 is coming due soon. Both of those are chapter 5 problems.
Yeah.
I did put chapter 4 more detailed answer sheet, if you saw that.
So we should be working on homework 8 at this point.
Yes,
And then homework 9 will be coming soon,
yes.
which is, yeah, still in chapter 5.
Yeah, we're basically in the middle of chapter 5. But any issues with chapter 4 homework? I guess that would be problem set 7.
I don't know if anyone started problem set 7.
The last.
So,
Homework 7 is chapter 4.
Yes.
Okay. So this next test is going to be over chapters 4.
5 and 6.
Okay, 4, 5, and 6. And obviously the principles build upon each other, so we obviously need a good understanding of that. But in the next test, might there be something pulled directly out of, say, chapter 2 or 3?
Not directly,
No.
but the concepts are going to carry forward.
Yeah,
You'll need those in order to do
Yes.
the homework and the test and the new stuff.
You'll get a lot of practice with this stuff as you go forward. Hurts the mind, doesn't it?
A little bit.
Just imagine how Tesla got all this just by observing it in his head.
Yeah.
You keep thinking it had to be by revelation. You need to do the same thing. You've got to study it out and ask for inspiration on it. The thing is, it works. So you've got to figure out how does the math wrap around it so that you can model it and predict what's going to happen. So no questions on chapter 4 homework.
As of yet, no.
Chapter 3 on transformers.
I don't think we're there yet.
All right.
Again, I think everyone's been so focused on the test in the lab, and then on top of that, today is a career fair here, last week was career fair down at BYU, and so it's just been a bit.
Okay. Shall we talk more about synchronous machines?
Sure.
Last time, I think we talked about the basic model of a synchronous machine.
We haven't talked about induction machines yet,
No,
right? Okay,
no. Let's get the easy stuff done first.
good.
Yeah. Induction machines,
That was also Tesla's brainchild.
yes. Very easy to build, very hard to understand. Anybody could literally build an induction machine. It doesn't take much. But to understand it, that's a real challenge. Okay. Generators. Synchronous machines operate as generators. The transformers have a lot of the same basic characteristics. Remember in a transformer, we ended up coming up with, let's look at it from a low voltage side. We've got our ideal transformer sitting here. We've got our magnetization and core circuit sitting there. Then we had our equivalent resistance and equivalent reactance. Then we had our secondary terminals. All right. Now, if you look at a generator,